Today we're going to talk about the NexCell Project Lithium Signal Soother, which first started shipping in December of 23, maybe January of 24, and to my knowledge is no longer being shipped. We are going to get into this. I've spent a couple months, even put a bounty out to get one of these, and so I have it now. I received it this afternoon, and I've had a few hours to look at it and, come up with this video. This video is going to be very technical. So if bunches of sheets of handwritten paper and even a spreadsheet that we're going to look at later are not things you're interested in, then here's the high-level overview. This product is dangerous to use. It has several dangerous design elements, and if you have this installed in your car, you should remove it immediately. This is not something you let sit idle. So we will talk about this in detail, but there's your clickbait intro. And let's start looking at this guy here. We're going to start on paper, unfortunately, but before we do that, I want to tell you who I am. And I've done this in the last video where I looked at the NexCell module. I'm going to do it again now, just in the interest of full disclosure. So I'm an electrical engineer by degree. I am a practicing electrical engineer. Electrical engineering is my life and my hobby. And those blend together, work, life, and hobby. So I've spent all of my professional life and most of my childhood even doing electronics. I've specialized in power transmission electronics, converting power from A to B, etc. I've released a product for the Honda Insight, which is a replacement lithium system that is safe for the Honda Insight to use. Whereas the Project Lithium, I have a previous video, if you haven't seen that, you should probably watch it, talking about why this is not a safe system. And there will be another video coming up with the latest hardware here once the bounty for that comes in. So let's look at an overview. Before we dive into the details here, for people who aren't as immediately familiar with what's going on in the system here, so let's look at the traction battery in a nickel metal hydride, for example, a Gen 3 Prius vehicle. So this has a traction battery. It's got a bunch of modules that are stacked together here all in series. And periodically throughout the nickel metal hydride pack, there are voltage sense leads, but there's not one for every cell. And for nickel metal hydride, that is safe. In my last video, people were asking, well, if nickel metal hydride did it, why is it unsafe for lithium to do the same? Lithium has a very, very different end of charge and when it's empty and when it's full behavior. It's very different than nickel metal hydride. Nickel metal hydride can safely be overcharged, particularly at lower currents. There's a chemical reaction that goes inside which continuously catalyzes and reforms, a hydrogen oxygen and then a water vapor cycle. So you can float charge a nickel metal hydride battery forever, essentially. And yes, there is a slow wear element to it, but it's very, very slow. Lithium is not that way. If you overcharge lithium, it will damage it. Even lithium iron phosphate, which these NexCell packs are, they're LFP packs, those are not safe to overcharge. Now, LFP is safer than an NMC, like a standard lithium polymer or lithium ion battery. When someone says a lithium battery, they're typically talking about NMC, and they will further specify if it's an LFP. And again, this is an LFP module, so it is safer to overcharge and undercharge because the failure mode, which still exists, is not going to be a runaway fire usually. It's not guaranteed, even with LFP. With NMC, if you overcharge it, you basically have TNT in your car. It's going to burn to the ground. Everyone's seen videos of that. So this is the high-level overview. We are going to get much more detail than this in a minute, but just to get everyone up to speed, let's look at the system. This is without the Signal Soother installed. This is just the OEM thing, how it worked. These were nickel metal hydride. If you installed the NexCell modules, it's still the same thing. You have these B0 through B14. They're tap harnesses, so they're basically periodically measuring, after, 5, 10, 15, 20 cells with NexCell, or with the OEM one, I believe it's every 12 cells. It doesn't matter. Just the voltages between nickel metal hydride and lithium are different. Nickel metal hydride is around 1 volt, lithium iron phosphate's 3 to 3.6. So anyway, you end up having fewer cells in between. So we have this harness, and this harness is hooked up to, you know, B0 and then B1, B2, B3. Now these are the modules. And so again, we're only measuring 14 points across the entire stack of, say, with the LFP, it's 70 cells, I believe, in series. And we're only measuring 14 series elements of those, and they're evenly distributed. We'll look at that more in a second. So then this temperature harness plugs into it's called the battery support unit, the BSU. In the nickel metal hydride pre-I, this is not a battery management system. It doesn't manage the battery so far. It actually just tells when the nickel metal hydride cells are totally shot. It doesn't have balancing or anything like that really in this the nickel metal hydride unit. When you put lithium in here, you don't replace this unit. Project Lithium has added a harness that plugs into this so that we can kind of tell if a cell is over or under charge. But my previous video was talking about whether or not this is nickel metal hydride and is safe, or is the Dr. Prius, the NexCell pack, which is lithium and is unsafe. That was my previous video. Now we're going to look at, you know, again, the signal soother, but we've got one other thing. So we are going to get to the signal soother by the bottom of this page here. So this battery support unit then goes to 4 temperature sensors. It measures pack current. It also does things like the HVDC isolation bus. I didn't draw that on here. And then it just has a serial bus. It's just an RS485, like a differential bus that it sends to the drive unit. So let's look more inside of each module here. So there are 14 of the NexCell modules in the Gen 3 Prius. Here's one of them. You can see it has 5 cells inside. They are series connected. And that I've drawn here. So this is each NexCell module. I should have written each NexCell module. The OEM modules there's 2 of them. There's 2 OEM nickel metal hydride modules for every NexCell modules, and they have, I believe, I don't actually remember, but the number of cells in the OEM. I'm not a Prius guy. I'm a Honda Insight guy. I am going in. That was one disclosure I should have made earlier. I am probably, and almost certainly at this point, going to be competing with a nickel metal hydride to lithium Toyota conversions. I have officially started that process now. Now, I did note, I did an announcement thread in this on the Prius chat. Haven't gotten any responses yet. Doesn't seem like it's as active of a community maybe, or I've just been ostracized for being a tall blade of grass here attacking Jack or whatever. There have been a lot of Jack is the Dr. Prius guy. There have been a lot of defenders, and I get that. You know, I am not doing these videos outright to attack Jack, even though I'm going to be a competitor of him. I'm doing them because the designs that NexCell has released that I have looked at are not safe. The first one is not safe. The signal soother is beyond not safe. It's insane. The decisions made on it, we'll get into them. But I'm just still doing the overview, and I'm not going to edit this video at all. I don't have time, to be honest. Spending a day analyzing this product is a day I could have done anything else, even if it was nothing else. But here I am doing this just because of this safety element. So yeah, more on the background of me there. So if we look at the modules here, here's one NexCell module. Here's the next NexCell module before it. You know, there's 14 in total, and so we're looking at any 2 of them. Here's what I was saying earlier, where we have these voltage sense taps. So say this is, you know, B7, that would be B8, that would be B9, for example, you know, wherever we are in the pack here. So you can see it's very clear we are not measuring every single cell. Lithium needs to have every single cell coming out and measuring it. Forgot that one. And so you can see that we're just not doing that. So what are we doing instead? So again, the reason you want to bring these out and actually have them go to a single computer, this battery support unit, this would be a battery management system if we routed every single cell out. We don't do that. Jack's NexCell module instead just has this little circuit board inside. This is a V1 one, and it plugs into here, and this gets shoved down. I've already talked about this again. See my previous video if you have questions about that. This is just a dumb, turns on at a certain voltage to balance the pack out. I don't know, it's total garbage. Previous video on that is there. Now, I am still, I'm waiting. I believe I'm going to get the bounty on the V2.5 hardware from someone who's going to send it to me. So that will be very cool. If that happens, I will look at that as well. The more I've thought about this, and because I did go actually look inside of a Prius Gen 3 for the first time last week, I actually think there is a safe way to do this now. But again, it's not up for me to design that. That Jack is going to need to figure that out. I'm not even going to describe it because, you know, again, I'm going to be a competitor, so I'm not going to design his products for him. Granted, the product that I make will not use this at all. Again, it's going to have a central thing. I'm going to replace the entire battery support unit, and it's going to become a battery management system. And of course, we're going to have to replace the harness. Here I am repping my own brand now. But anyway, if we route all of these cells out, then we have a single computer, this battery management system it now becomes, that can look at every single cell. And once it can do that, it can make decisions based on every single cell. So if a cell gets full or empty, it can tell the car, hey, stop charging, something's wrong, you know, however you do that. So, traction battery overview, inside of each module. What does the signal soother do? The signal soother, you unplug this here, and you plug the signal in between. And so that's kind of what this is. You know, this plugs into the battery here, and then this goes and plugs into the battery support unit. So now we have this signal soother. It's still only looking at the 14 taps because this is just a man in the middle. And before I saw this in person today, I'd seen a picture of it online, and it was immediately obvious to me, just because of my design experience, that this was just a bunch of you know, op amps doing something. So we have our input, we do something to it with an op amp, and then we output it, something has been done to it. So I had a couple of theories on what it is that we were doing to it. My first theory was that this is a low pass filter. You know, we have some noisy signal coming in, and that's causing fault codes. I suppose I should talk about what the whole point of the signal soother is here. The signal soother's point is to make the battery support unit happy. And the way you make the battery support unit happy is you represent all of the deltas between every single module as the same. Another way to think about that would be if this is, you know, an 18 volt module and that's an 18 volt and they're all 18 volts, battery support unit's going to be happy because it thinks all the cells are balanced. If this one's 18 volts and that one's 14 volts and this one's 13 volts, you know, I don't know what the actual failure condition is, how many volts it is, then that's going to be problematic. Now, fundamentally, if that happens, that means something is wrong with your pack, right? Under normal conditions, no matter what the pack voltage is, all of the cells should be balanced, whether it's 3.5, 3.4, 3.2, 3.1 for lithium iron phosphate cells. The signal soother is fundamentally unnecessary just in the abstract. If the pack is in good health, the signal soother is not required. If the pack is in bad health because it's poorly designed, then the signal soother is only a band-aid. I think it should be called a signal faker or a signal averager instead, and we'll look at why that is. But anyway, that's what the signal soother is trying to do. And again, I had some theories on how it is that we were making it happier. And one of them was to do a time averaged low pass filter, you know, where we take these large deltas and we make them smaller. I didn't know if that was the issue. Again, before last week, I'd never even been inside of a Gen 3 Prius. Another option I had, or thought I had, was that maybe it's some kind of gain and or offset compensation. So if this is our actual voltage on the input, so coming out of the battery, we're looking here. So this is, again, theoretical. This would be the voltages here, and then here's my theoretical output, and then here's another one. This is a different, the X and Y axes have changed. So this one was time versus voltage because we were looking at a frequency domain thing, or you know, a signal noise thing. Here we're looking at the actual time, or the V in versus the V out. So here, if the pack is 18 volts, this is the OEM. So if the pack is 18 volts, it's going to say 18 volts because in the OEM configuration, again, there's nothing there. We're not spoofing it, but just again, hypothetically, the signal soother might have been taking 100% of the voltage and making it 80% or 75 and 60%, some kind of gain and or offset thing. None of those were the case. And these were like, okay, fine. The low pass filter in particular, I was like, okay, maybe that's okay, especially if it was a really low pass filter, like over 5 or 6 seconds, but it's not that. So I went and took on our signal soother here, I just picked V5, and just some commentary on this circuit board. This circuit board is not laid out well. There are traces on this board that go somewhere and then just stop. There's no via, they don't go anywhere. There are also some high voltage violations. The most egregious theoretical one would have been a V14 to, B0 or V0. But actually we avoided that because this trace, I think probably just by the luck of the draw, ended up being on itself. It's got the 3 millimeters of clearance. Now that's not the case everywhere. There are certainly inter-pack voltages, say, again, hypothetically here, from like B12 to B7 or whatever. We have a lot of traces crossing over here. There is a conformal coating on this board, but it is not reputable, I would say, conformal coating. I was able to remove it very, very quickly with just a Q-tip and 91% rubbing alcohol. Rubbing alcohol really shouldn't immediately attack a conformal coating. Acetone will, and those are actually very similar chemicals. The compound is very, very similar, but I'm not going to comment any further because I'm not a chemist. But I do know that they are very similar chemicals. The acetone should attack and remove a typical conformal coating. The rubbing alcohol should not, and in this case it did. Now rubbing alcohol will eventually separate the layer, so it'll separate from the PCB membrane to the actual the conformal coating, but this immediately attacked and removed, so that was interesting. I then removed V5, so my first thought was that these silk screens, they're labeled V1, V2, V3, 4, 5, etc., all the way up to 14. They're up to V13, and that is important here. Remember, there are 14 voltages we're spoofing, but we only go up to V13 here, so we'll look at that in a second. So I took this guy off so that I could properly characterize the circuit. And this was my first attempt. Here's all the parts I removed here just to see what they were. This is just a Burr Brown OPA 251 UA op amp here, as I had theorized it was an op amp. And this is just, the run-of-the-mill. It's one you would learn about in a textbook. I had a tech lead in a former life when I worked for someone else. And he would always ask, one of his favorite interview questions for potential new hires was, what's your favorite op amp? And this was one where if you mentioned the OPA 251 or 241, you would immediately, it didn't matter how well you did in the interview, because that just means that you'd never use an op amp because this is the one you use in college, whatever. But you do, anyway, I don't need to get too far down a tangent there. I will note this is not a rail-to-rail op amp, which is problematic for this circuit, but it does seem to work well enough that you get some compression as you get to the V positive, because there's a V positive minus 0.8 volts because of the diode drop, at least for the specification. And it's not too important because even if you have an error, it's going to be constant across all of these. But I just did note that was kind of interesting there. So if we look at the circuit, this was my first attempt, kind of drawn as I saw it on the board here. You can see here, this is an interesting thing, and we'll develop this a little bit further. This circuit looks at B4 and B6, does not look at B5. So B is the inputs here, they call it the batteries, the modules, whatever. It's these inputs right here are on the bottom, and then the outputs are on the top going to the battery support unit. So the outputs are here, the inputs are there. So inputs, the things from the battery, and here's the spoofed signals that this thing is spoofing here. The fact that there are 4 connectors is simply just that they could have had one connector on the end, and just because of the pin counts, they didn't. Note that I did color code these just so I didn't mix them up. And also note that the labels here are not the same as the labels on here. The pinout's different. I typically don't like changing the pinouts, the names, the trace names from at the connector. In this case, I think it's because they want to make sure they get the correct pin number in the connector here. Whatever, that's fine. So where are we going with this? Yes, we don't look at, I just hypothetically, or I just looked at I just picked V5 out of random. So this is ultimately spoofing the V5 output, and that's here, J2, which is this connector, and then V5 is the one marked V5 there. I've got it circled. This is the first one I looked at. And we are spoofing V5, but we're not looking at the battery 5, so that was kind of weird, and I definitely was like, oh, that's interesting. Let's look into that more. We have a pretty typical here B6, so we're powering this. We have a 1K resistor here just to probably limit the inrush from these capacitors, and this doesn't pull that much current. I actually calculated that. We'll look at that later. And then we have, this is already looking like an inverting type topology here, just looking at the way these signals go. This was a little interesting. And then, so our ground reference for this is B4. And again, we're just looking at the V5 output. And so we look at B6, B4. We do not look at B5. Now, I have an asterisk on the next page. We do use B5 later, but just not on this circuit. And we'll look at that a little more in detail. So already we can tell this circuit is doing something interesting. So next I took this and I just tried to conceptualize it into a more of an engineering, you know, what you would typically look at here. So this J1B6 is the same as that J1B6. The circuit's identical, it's just drawn in a more typical, this is visually what does it look like on the board. Here is how an electrical engineer look at this here. And you can see once again that we have our J1B4. Here you can see where I put some exclamation points here. This is where I was like, oh God, this is just a voltage follower. We have this weird output load, this 2 nanofarads on this, this pole on this op amp is probably saved by the 1K thing. It's probably browning out a little bit as the voltage changes, which hopefully it's not changing very quickly, right? Your battery voltage should change very slowly, but this is certainly a pole on your op amp, which could make it unstable. Now, of course, it's a voltage follower, so you don't really have any gain, so you're probably well within the gain bandwidth product. However, we don't have any filtering on the input, so these are just nitpicks, things that I would have done differently. So next page is the same circuit, but the one that I was going to show on video, and then I decided to show the other one as well. So here's what we ultimately have. We have B6, and again, we're just looking at the V5. This is the one that I looked at first. We're going to abstract this into math here in a second, and then this circuit will no longer be important. So if you were just lost at this point, hang with me for a couple minutes, and then we'll be down here where we're doing simple division and addition and subtraction, and you know, that'll be a little bit easier, still in depth. Again, this is, I made no promises this is going to be an easy video to follow. I want to get the technical aspect of what this device is so we can draw conclusions about what this thing is and the company that designs it. So B6, B4, again, B5, the fifth tap voltage we're not looking at that at all. So if we were to look at this in the pack, we would have a module right here, and we'd have another module right here, and each one of these modules has 5 of these cells, so maybe 1, 2, 3, 4, 5. In this case, it would be, let's see, V5 would be 21, 22, 23, 24. That might not be right, but it doesn't matter. It's close enough. 7, 8, 9, 30, so 27, 28, 29, and 30. So we have this tap here going to B5, and then we're going to the other cells down there, the other modules down there, and then the other modules up there. But the important thing is we have taps here, we have a tap there, and we have a tap there. That's what we're looking at. Now we're not looking at B5 though, which is very, very interesting. So if you look at this here, even just looking at the power for this thing, it would appear I didn't draw this one line. Yeah, I think that's right. Yeah. Hold on the fly. I'm not editing this video. Honestly, guys, I don't have time to. Yeah, I have a lot of stuff I want to do before I die, and this is not one of them. Okay, yeah, so sorry, I didn't connect that signal, but it is now. Something seemed off. Anyway, so if we look at this, the addition, if we were at 3.6 volts per cell, then we're going to be at, 18 volts per thing, and then 36 volts here. I'm gonna pull up off screen here. You'll have to bear with me, just so I can get it, because I'm just kind of realizing this right now. That's 36 volts differential. And let's find the voltage max for this guy. Interestingly, they don't have it on page 1. Sorry, I know this is not, okay. Okay, so the 251 absolute maximum operating voltage is 36 volts. So this is used when the pack is at 3.6 volts per cell, is at the absolute maximum. Now, typically you would want to stay way away from the absolute max voltages. So that's interesting. There's another issue. We're running these op amps way, way, way too hard. Okay, got to stay on track here. I actually made a list of stuff to talk about. It's taped up there because I will ramble. I'm still rambling, but I got to stay on track on this thing, keep this video under, I don't know, 40 minutes. We'll see what happens. No promises that's going to be the case. So where were we? Yes. Okay, so we're looking here. We have a 36 volt across this poor op amp. There is a 1K that's limiting the, there might be a small voltage drop. Probably not. We could actually calculate that because I did the math here. 30, yeah, no, there's almost no drop here. It's millivolts of drop across those. Maybe it's certainly under a volt. I'd have to do a calculator there. Anyway, yeah, so we have a diode here. This diode is just so that as you're plugging the connector in, we don't have any overshoot. This might be a Zener, I don't know, I didn't actually look at it. It's 0.7 volts when you forward bias it, but I didn't do a breakdown voltage. It's probably a Zener. It doesn't matter. I still have it. I have it taped onto here so I could look at it. It doesn't matter for this circuit. This is a voltage input protection when you're first plugging it in and unplugging it thing. So here's what we're doing. B6 to B4 has this permanent 2 mega ohm resistance, and so we are always drawing power whenever whether car's on or off. It's actually a really small amount of power, but I definitely just noted that this is a constant drain on here. This is generating, I called it a pseudo J1B5. So this is a pseudo battery 5 voltage. Again, we're only looking at B6 and B4, and we're generating a pseudo B5. And then we have a 100 ohm resistor here. Why? I don't. If you have a mega ohm of resistance here, this is your B6 minus B4. Anyway, that seemed unnecessary. Maybe that was just stuffed because maybe that needed to be disconnected. There was no alternative circuit here. This component is completely unnecessary, particularly, oh my goodness. Honestly, if you're going to waste the board space on this, you should put it here instead. It's not there. You should put a 1 mega ohm there so that the input impedance is the same on both of those. That doesn't, whatever. This works, but that just seemed unnecessary here. And it's just a voltage follower. So what is this outputting? It's literally outputting our pseudo J1B5. Here's our 2 nanofarad. So yeah, here was our total power consumption is 702 microwatts. It's very, very low. But it's always going there. Okay, yeah, so if you have tuned out, here's the point where you tune back in. Maybe you catch an anchor here, and then maybe you get lost again. Don't know. I do care, but again, this is a technical video. So here's what this boils down to. This entire circuit is equivalent to your battery VN J1B6 minus your battery VN J1B4 over 2. And so this is a plus. Yeah. This would be a plus, but anyway, we're dividing. Hold on. JVN. I did this in absolute, but if you did it in delta, it doesn't. No, this is right. Hold on. Got to make sure we do this correctly here. This would be plus, and then this would be minus. Yeah, that's a minus. Yep. Okay. Sorry. It's getting pretty late here. This is correct. Here's what we're doing. We're averaging the voltage here. Divided by 2. Yep. This is, yeah, because it's 6 and 4, and we're getting, yeah, because this is absolute. Sorry, I'm in an absolute versus a relative frame here. This is absolute voltage. So this would be 0 volts or wherever we are in the pack, 100 volts, and then this would be 118 volts, and this would be 136, just theoretically or whatever. In absolute frame reference, this is correct. It would be that voltage, 136 minus 100 volts is 36 volts divided by 2 is 18. So yeah, if this were relative, then you would want to add those, which is interesting. Anyway, so here's our Vout. It's a spoofed Vout. And putting this in words, and then we're going to look at it graphically here. Everyone loves a picture here. The signal soother averages the voltage between, it's not adjacent, it's each odd or even input stack voltage. And we'll look at that here. That's what these highlighted colors are. And so another way to put this is it hides the voltage imbalance between the taps. So when you look at this, I meticulously pinned this out. I wanted to make sure I didn't make any mistakes as far as what this schematic is. When you pin it out, you look at the V1. So this is the op-amp silkscreen reference designator. It's titled V1. I thought first these should be U1 for an IC, but they're V1 because it's the V1 output. So that's this V1. Here's V2. Here's V3. Here's V4. Here's what each one of those are doing. Each one of these, we looked at V5. Here's V5 here. That was B6 minus B4 divided by 2. That's our V5 output. And you can see they're all the same with the exceptions of the in pieces. And the reason you need to do that is because we're looking at an N+1. at battery 14, there is no N+1. There's no module 15. So how do we get that voltage? We literally directly short it out here. So the input here on B14, wherever it is, I don't know, yeah, I can't read this here. Here's B14, it's literally shorted to the output right there. Same thing for B0. B0 is directly shorted to V0 there. So what is this? This averages, but it doesn't average in with N-1. It actually averages in every other pairing, which is interesting. We'll look at why that is interesting electrically here in a second. But first I want to show this to you graphically so that we can play around with it. So I'm going to do that on the computer. Here's where we are now. Again, apologies if you were lost. I'll give you another anchor here. And it's literally just my laptop because I'm not going to be doing screen captures on this guy here. So I've done a hypothetical thing here where I have 14 NexCell modules. Each one has 5 cells in it. So here's cell N+1, N+2, N+3, N+4. Those are the 5 cells inside of each module. So for example, module 1 is on the left. Module 14 would be way over there on the right, and there'd be a bunch of them in between. I've put some hypothetical voltages on here so that we can just see kind of what happens here. And we look at the output here. This is the BMS wire, the actual output. So so this is without. So the top one is what is the actual cell, the actual module voltage. That's these wires here. And in the case of the OEM, this is what the output would be as well. Now with the signal soother installed, this next row is what the signal soother is doing to those voltages. And you can see that it's averaging them out. So if we look here, we have one imbalanced cell in every module here. Again, this is just hypothetical data. I'm going to take here, and I do apologize, the color coding on this, the conditional color formatting, can be a little bit wonky. So like 18 volts is the same as 18 volts, but just bear with me on that. This is one of the consequences of using open source software. So these are identical here. The important thing to look at right now, let's go ahead and we'll just stuff that module 4 has a 4-volt cell on it. And again, this color coding is not quite correct here. It should be red. Doesn't matter, we're gonna ignore that. So let's look at what happens when we put a single cell in that's messed up. So you can see that on module 1, the actual module summation is 18.4 volts, but we're outputting 18.2. We have soothed this signal. This is a permanent modification too. This is not a temporary thing. So if we add this 4-1 here, you can see more what's happening. We've taken an 18.4 volt on one of the sense wires here. So this one sense wire did have 18.4 volts on it. Now it has 18.2, and its neighbor below it has 18.2 as well. Let's see if we can put 4 volts here. This would be an overvoltage cell event. So you can see the same behavior now. All the colors are correct right now. We get this 18.2. Now this signal soother works on all of the modules except for module 14. Because there is no module 15, and because we're doing an N+1, module 1 is based on module 2 minus module 0, which module 0 is module 1 minus. We actually get soothing here. But on module 14, because there is no module 15, we don't have a reference voltage higher than the HVDC positive. So actually any error on module 14 will carry through. It will also carry through to its neighbor as well. So in the case of module 14 only, it actually makes the circuit worse overall only on module 14 because we get the actual error here, and we also get a small error on module 13, which is still doing its averaging thing, the N-1. Now what happens if you get multiple cells here? So you can see that now we have 2 modules with cells that are very high, and you can see that we have 18.2, 18.2, and 18.4. So we now have to have 2 failing modules in adjacent, 2 failing cells in adjacent modules before we get the same behavior. So the cells have to be failing worse. And that's the key takeaway to why the signal soother is unsafe. We're taking what before we could measure every 5 cells. So before with NexCell, we could measure every 5 cells if there was an issue. So like if you have one cell here that goes bad, you saw the 18.4 volts there. Now we're hiding that. We're making it half as bad, and it gets worse as the voltages get worse too. So let me change this back to 3.6. So the point of the signal soother, and you can see it graphically here, it takes large deviations and makes them smaller. So the one red dot is hiding underneath the blue here. You can see the 18.4, those are the same. If we made this, say 3.9, that might duck down, yeah. So anyway, that's kind of the gist of what is happening here. It's not good. We're taking what before we had 5 cell resolution and we're making it 10 cell resolution. So we're literally averaging out a bad cell over 10 cells versus averaging it out over 5 cells. And so we've actually gotten even less resolution. It's wild. So let's just hypothetically here, I'm gonna take this guy, the 3.6 here, and I'm gonna just kind of start over with a blank state here. Oops, that would be unsafe. I don't know why we did that. Let's see. Okay, so our color formatting does go away. Let's say we have one cell or one module where, let's say you had a module go bad and maybe you replaced it and it's got less capacity or more capacity. You can see the huge issue here because these modules are different voltages, whereas the battery support unit sees 18 or should be seeing 18 volts on all of these, except for it's 19.5 volts, which is way overcharged. LFP is maybe 3.65 volts max, although really you shouldn't be pushing it that high. But whatever. We're 1.5 volts high. Wow, the battery support module is going to throw a huge error, right? It's really unhappy. You're going to get check engine light. Well, now we've averaged it out over 2, and this is an extreme case. But now instead of having a 1.5 volt delta, we have a 0.75 volt delta. So we've averaged that all out. Now, I mean, that's it, basically. What are we doing? We're literally averaging all of the even input voltages to generate the odd voltages, and then we're averaging all of the odd voltages to generate the even voltages. Yikes. Okay, so let's circle back the bandwagon here and let's just talk about what is unsafe here. So one, the major unsafe thing is that we're masking the over and under voltage condition on charged cells. Instead of being able to have resolution every 5 cells, we're now only getting resolution every 10 cells, except for module 14, which is still 5 cells, because the kludged circuit here didn't actually end up working properly. So anyway, I should cut this short. The first issue is that we're masking an issue. We had a fundamental design issue by reusing the OEM battery support unit rather than generating and designing a new one. Again, that's what I'm going to be doing so that it's safe. So that's, of course, the first major issue. That's why you should throw this out if you have it. The second issue is that this defeats the safety aspect behind the service disconnect. So the service disconnect, if you're not familiar, on the Gen 3 is between 4 plus and 5 plus, of course, yeah. 4 plus and 5 plus. And when you pull that out, it breaks the pack in two. This circuit's always connected, so when this is connected, when you pull the service disconnect plug out, you still have high voltage. Now, granted, it is across a large resistance just because of this 1 mega ohm resistance here, but you also have a 1K here that is bleeding through. It's pulling about 50 microamps or whatever. It's dangerous. When you pull that service disconnect, the goal is to make it safe for the operator. When this is plugged in, the service disconnect's primary feature that you split the pack in half is compromised. Now, granted, again, it is through a high resistance, but it doesn't matter. When you're doing high voltage, high resistance is not a safety issue. It doesn't make it safe, rather. So, yikes. And a consequence of that as well is if you try to turn the key on with the disconnect removed, say you're troubleshooting and you forget to plug it in, you're going to break this in 2 spots because you're going to get the full pack voltage across on the Gen 3, the 4 and 5. So somewhere about here, you're going to blow up V4 and V5. And yeah, anyway, so there's another issue here. And then, of course, the creepage and clearance on this PCB, I kind of mentioned that briefly. This is high voltage. This is directly connected to the battery. There's no fuses on this. The traces would have to burn, I suppose. And then this is, again, it has a conformal coating. It's not very well applied. And then it's just put in heat shrink. And then it's literally just like stuck in the car, like between the metal chassis right by that battery support module. And yeah, talk about ways to burn the car down. So anyway, and then the traces too, I mentioned that earlier, but these traces just run into each other. So yeah, that's the long and short of it. We're right here at 40 minutes now. If you have this signal smoother, this dumb device installed in your car, this fundamental misunderstanding of what safety is, remove it immediately. Don't drive your car. You're just asking for a problem that was already bad. This, and specifically this, or the lack of a battery management system, you're making it worse, twice as worse, in fact, except for Module 14. Module 14, you're still safe when this is installed. So anyway, I'm done. You know, I will mention that there was some additional, this is over that, a little bit of tape, some element of safety. This was not enough. Conformal coating was terrible. The design is terrible. The whole thing is terrible. It's just terrible. Don't use it. Oh my gosh. Like, as always, I guess. Thanks for watching. These are not products that casual hobbyists should be designing. These are dangerous products that can kill you if they are unsafe. This is unsafe. This is a fundamental misunderstanding of what safety can be. Anyway, thanks for watching.